Oh, hey. So this is what the fork is happening with Node.js. So I was like, what the fork is that? Might as well. So my name is Karissa McKelvey. This is my first JavaScript talk ever at a JavaScript conference. So what the fork is that? Let me see if I can actually go to slides. Okay, cool. So we're part of the US Open Data Group, which is usopendata.org, and we are a nonprofit. So that means we're funded by the ALFRED P. SLOAN Foundation to fix science. That's really hard. But that also means that I'm a professional open source software developer, and I don't have to get customers. I just have to write grants, which is kind of the same thing. So I first came from doing Twitter research. I was a PhD student, and I dropped out because you should do that. So I was studying these really awesome political conversations about social movements and elections on Twitter. We were able to predict elections, see who was a bot, and these sorts of things. But I was also in charge of, most importantly, collecting and cataloging data and doing data visualizations with JavaScript in 2011. That was fun. But really, the problem was, how do you collect and store all this data? And how do you get data sets, which are like CSV files, to people who have never programmed except for like a little bit of an Excel file or something, or people who use R most of the time, or Stata. It's really hard, actually, to be able to say, here's a data file out of this 4 terabytes, here's like a really small thing that you asked for. And I don't have SQL, I don't have any of this stuff, I just have to give this data file to you. And this person, they're gonna wanna know where the data came from, where the data's going, and it's really hard to collaborate with them. And so, I was really, really interested in this problem because I saw it everywhere. In biotech, it's a rule of thumb that half of republished research cannot be replicated. So that means that people, they get this data file from a person like me, who's a data engineer, and then they're like, well, I don't know where the data came from. Oh well, and nobody else can get the data again. And this has been going on for a long time. It's a problem also in psychology. This was a big thing that happened in Nature this fall, if you heard about it. So why is this a problem? And this is the thing that I've been kind of obsessed with for the past few years. The first problem is that code and data is private. So when a scientist is doing research, they'll often not put it on the internet, and that's for good reason, either because there's privacy concerns surrounding data, or they're too nervous to put their code online. Code is hard to install, so often if you're trying to install stuff, you're trying to install some C stuff, some Python stuff, you might have some JavaScript thing that you have to run, like have a visualization, it's like all really confusing, and they're scientists. Deployment costs money, so MIT comes out and they're like, you just put this thing on Hadoop, it's fine. And then everyone's like, I don't have Hadoop, I don't know what I'm doing. And that's hard to do, and sometimes the code and the data is just lost completely. So I know what you're all thinking. This can all be solved. You just use GitHub, it's fine. The problem is that this actually destroys all scientists. Scientists cannot figure this out for the life of them. As soon as they hit a merge conflict, they're like, screw it, we're not doing this anymore. So how do scientists reproduce research if they're not using GitHub? Some of them do actually use GitHub, I'm not saying they don't, but they want to reproduce research. And more importantly, the way that we define the problem is not that they want to reproduce research, but how do data scientists in general collaborate? Because when we're really talking about data being transferred from one place to another, being visualized, we're really talking about collaboration between people. And what they usually do, and this is like standard practice, is they put data on one drive and everybody accesses it at the same time, well, hopefully not at the same time. Or they put it in Dropbox, and or they email it to someone, email link. My favorite is like mounting Dropbox into AWS. This is actually standard. This is what data carpentry teaches. So domain experts aren't developers, okay? They're mathematicians. They're looking at whiteboards. They're studying pollution in the ocean. They're looking at the stars. They have terabytes and terabytes and petabytes of data that they want to sift through. They don't want to be doing this, okay? They don't want to be looking at like, why did my thing not start? Someone else's code. I gotta like go and search on the internet and like, okay, because that didn't work. So I gotta like, I don't even know what this is. I don't even know what this means. So we don't want them doing this. Git is for source code, and that's okay. It's okay. Git is for source code. But we need something like Git for data for these kinds of people who do data visualization, who are really domain experts in their field. But how do you build a frictionless Git-like tool for data? So when I say frictionless, what I really mean is something that's easy for even, a domain expert that knows a lot about biology, they can use, and then even a developer, someone like me or someone like you, can come along and also work with that data. So what I mean is people working together to produce or create something. And what that means is really computers being able to work together. So the tool should be simple, but simple doesn't mean easy, right? We're not saying that it's just going to be like you type in 2 commands and everything works. But it should be simple to use on the developer side and simple to use on a domain expert side. So why did we pick Node to build this kind of tool? And that's a good question. So first is C library integrations. So the LevelDB integrations in Node are fantastic. It's really easy to just create like something with AbstractLEVELDown. How many of you have heard of AbstractLEVELDown? Wow, no, okay. So AbstractLEVELDown is really nice because it gives you an interface for doing database operations. So I can say put, get, delete. If I just implement those 3 things, then I can interact with any database. So a lot of people have implemented these kinds of things for the file system, for MongoDB, for some SQL variants, like every SQL variant, for Google's new XYZ thing. So there are things that you can use, and we really like this because we could develop on top of AbstractLEVELDown using JavaScript, and people could use DAT anywhere, in the browser, at Google, on their file system locally, somewhere in the cloud, et cetera. So, for example, a way to use this, like this is a fake module called BitTorrentDown. Assume it probably works, or if it doesn't yet, Matthias is probably building it right now. So in theory, we really want to be able to make it really easy for you to say, I want to use a DAT storage thing, and I want it to use BitTorrent, and then I just give the one thing to the other thing, and now you have a BitTorrent-backed storage. Modularity, so it should be separate components. So this is what I'm talking about with this sort of thing, where it's really easy to just plug and play like a different backend or something like that. So we really like Node's ability to do that with CommonJS, I guess. Command line and detection, an Electron app. So we can have, in Node.js, it's really easy to make a command line app, but it's also really easy to make a desktop app that's cross-platform really quickly. So we're only a team of 3 people, and that makes it really hard to do something like a cross-platform app, but that's really important if we're going to do work with scientists. Most sociologists use Windows, and most astronomers use Linux. So we have to have something that's easily cross-platform. It should just be really easy to install. And streams first. So we're working with potentially really big files. One of our first pilot projects was in astronomy. So you're talking terabytes and terabytes and terabytes of data. And if the thing stops working or your internet connection goes out, you don't want to lose everything that you just tried to download. So we really wanted it to be really good streams first with resumability. And Node has a really good streaming asynchronous interface. So I can do something like listen on a diff stream. So I can say DB is my DAT, and I can say create a diff stream. So when someone else pushes their code, like to the DAT, I can just listen to that, and in my app, which is like a data visualization or something, I can listen to those changes and do something with it. So let's go an example. So I have a picture of an ant, and when you do when you try and like see if this picture of the ant has changed, what you really want to do is look at the contents of this picture. So when I look at the context of this picture, so say I have this ant fs read file sync ant.jpg, make it toString, I get this, right? It's just some random gibberish. But if I make it do a hash function over this, what it's really doing is taking every byte in the file and putting it into a hex digest, and it turns into this. Every time I do this, as long as I don't change ant.jpg, I'll get the same thing back, right? So I know that this is the same exact file that I got the first time. And if anyone changes this file, and I run this function again, it'll be a different hash, right? So this is kind of the basis for how Git works, and this is the basis for how Dat works as well. This makes it really nice. So if I say, I mean, I'm going to say we're pretty familiar with Git, so I'm just going to go over it really quickly. But if we have 3 nodes, say we want to do a merge, and we have C, which is cat.jpg, B, which is bunny.jpg, and we want to add A, which is like the new head node that comes from B and C, what we would do is we have to compute the hashes of bunny and cat and put that into a new hash, which is A, with the hash of ant. And this is what we call a Merkle DAG, a Merkle-directed acyclic graph. So what's actually happening here is that in order to compute A, I need to know the contents of bunny.jpg and cat.jpg. So you can't fake it. Like someone can't fake my data and say, oh, I'm going to push to you some data. They have to actually have the data that you push to them first. So this has been around since 1979. Mr. Ralph Charles Merkle, I'm sure he's a doctor actually. But you know, the basis of this is that there are no cycles. So it's really important that we just establish that. And all these things use it. I don't know if you know IPFS, but that's the bottom right. I don't know why there's no IPFS. But we all use the same thing. So when you have these like really complex structures, hashes pointing to each other, what we do is we take pointers to the data at the end. So like the hash is not necessarily part of the data, but it could be. And I'm going to talk a little bit more about that later. I think I'm running out of time. So say we have the DAT, which is DAT graph. This is actually a brand new module, and you can go check it out. Say I'm going to have it in LevelDB. So I'm using LevelDB, just like a local file system, as my storage. I want to add a node to the graph. And I want to add it as like the parent node, the head node. So it has no links. So if you see node equals links and it's an empty array, that means that it's the head of the graph. And so I can say dag.add node, and then I get this hash back, and this is the head. Then I can add a node after it. I just point links. I have it point to the head as one of the links, one of the parents. And what it does is it's taking this node.value, and it adds the value's length, which is something that we call framed hash, and the hash of the head. And then so we get a new value, a new hash, which is the new head. So this is great. This is easy. It works like Git. But what about conflicts? So what makes that special? Like, why am I talking about this? So when we go back to the thing that says the tool should be simple, right? There are no conflicts in DAT. And you're like, wait, but there's conflicts in data, so how can there be no conflicts in DAT? Well, we actually just treat them as forks. So this is actually something that Substack hat tip really was, he really pushed us to do this, which is that we have 2 forks in the graph. And if I pull or clone this graph, it doesn't actually prefer one or the other, right? It doesn't force me to merge them if I push this to someone else. Like Git, if you don't pull before you push, it says you can't push to this repository because you have to resolve the merge conflicts. And it's a huge problem for a lot of people. Like resolving merge conflicts can be like a huge pain in any sort of deployment scenario and collaboration scenario. And we just kind of remove that entirely from DAT. So but it doesn't mean you can't merge them. So if I still want to merge them, I can. I just provide 2 head nodes, or two parent nodes in the links. And I can say, I'm merging these 2 things. And here's the new node for the merge, say. So what this is actually really doing when I add a node is it's creating a framed hash. And for each of the links, it's adding that parent link. But okay, so I say like I'm doing sha.update node.value. And if you're thinking about this, you're probably like, well, if the value is like a 3 terabyte file, if you do the hash of the 3 terabyte file, that's like a lot of hashing. And that's pretty bad, actually. That's really slow. So what is node.value? In Git, they actually do that. They actually hash the entire file, and that's why Git is slow. Once you try and add, like a terabyte of data to Git, just like don't even worry about it. You're never going to be able to use that repository ever again. So Git LFS is trying to fix this problem. I don't know if you're familiar. It's a large file system. So what they do is they actually do a pointer to the file, and that file is an S3. So it's actually a direct. You're like kind of baked into the GitHub system. Dat, on the other hand, is a little bit more flexible, and it's a pointer to whatever you want. So what we do is we do either a file or a list of files. So it actually could be the entire state of your file system or entire state of a folder, and that's where it works a little bit more like Dropbox. So in Dat, each graph node points to the data storage. So what I'm talking about here, I'm saying a pointer to a file or a list of files. Pointer to a file or list of files, I'm really talking about a pointer to like some data storage place. And this is where it's really open-ended, and that empowers people like y'all to build something really cool on top of it. But it also makes it really easy on a default level, because we can just say, oh, it's the file system by default. But it could be anything. Yeah. So one of the cool parts would be if we had like a BitTorrent tracker. And this is something that I'm actually really interested in building right now, where you have data that is served by people. And BitTorrent is just a hash, right? So if it's just, I want to serve this data, and someone else downloaded that data, why can't they see that data via BitTorrent? It would make something really fast. So another way you could use it is to store the data entirely differently on different computers. So I could say, when I pull this data in, it's actually going to be in Postgres, but maybe my data scientist is actually, it looks like Dropbox on their machine, right? So they're just pushing CSV files. But when I get that new data, I'm putting it in Postgres. So how does that actually work, though? Like, if that person is pushing data to Dat and like I'm replicating it on a different computer or a cluster, how does that actually work? So if computer 1 wants to push a new merge, or say that merge that we just had before, they want to push that to computer 2, say. So computer 2 is like, hey, I want that node. Computer 1's like, cool, I'm going to push that node to you. So they're saying, okay, push dat.computer2.edu. What computer 1 actually says, okay, when I'm pushing, I'm actually going to tell you all the hashes that I have in my graph. So that's a really easy, just like iterate through all the hashes. Computer 2 says, okay, cool, from those, I have these. And so if you look, it says 11110. Just to make this like really, really simple and really, really easy and fast to like transfer this first handshake. So like it would say, yes, I have A, B, C, D, but I don't have E. So then computer 1 knows, okay, oh wait, how does computer, oh yeah, this is a good point. How does computer 2 know which ones are missing? So that's actually something that you can figure out yourself, probably. If I don't have cycles, oh, binary search, right? So maybe I say, oh, I'm trying to look for this hash. I'm trying to look for C, C, D, E, F. Okay, I can just like go and actually look for that using binary search. So, but really it doesn't actually matter. So I could actually look for this hash any way I want to, which is the beauty of doing this in a modular fashion, is that if you're using an enterprise or with a really big team or really distributed teams, you can kind of choose as long as you're implementing that, as long as you're implementing that reply in the right way. So we separate the replication protocol from the on-disk format from the graph, which we give great defaults for, but it's not, we don't like bake anyone into it, so it really makes it really nice if you wanted to implement this on a browser or something. So computer 1 is like, okay, so here's what I didn't have. So they finally send it back, and they actually are sending the real value of whatever it was that the other person didn't have. So then you finally have the graph, and you don't have this problem where I'm git pulling rebase origin master, and then everything is broken, because I can actually just push whatever they don't have, and we actually have a way to talk to each other in a general way. So, and we could do this over HTTP, WebSockets, SSH, carrier pigeon, your choice. And we obviously support all these three at the top, but we want to make it really easy for people to replace them. So our defaults, we have .graph, which is a level DB, backed, which is like on your file system, binary search, Merkle DAG. The .blob store is a content addressable file system, so it's actually just storing it directly on the file system in a content addressed storage. This is kind of like BitTorrent, so it's really easy to find like what kind of piece of data you want. And you can look that up a little bit later if you like. That stream replicator is like sending the protobufers, so we actually take the metadata and put it into protobufers, which is a really nice alternative to JSON, and we put that over HTTP. So we have a generalized and modular Merkle DAG for everyone, where we give good defaults, and it makes it really easy for people like you to build apps on top of. So what's the feature like for DAT? Like what kind of apps am I building? So a lot of what I do is I'm talking to people like you and building apps for DAT. So one of the things that I'm really excited about is building stuff on like BitTorrent, like I was talking about before, or doing stuff on the blockchain maybe, I don't know, that would be cool. And Google Sheets. So one of the things that really bothers me is when I have to interact with people who are using Google Sheets all the time, because it's really hard as a developer to know when that data has changed and how it has changed in the past. But it's really, Google Sheets is really nice for other people who want to be able to like, you know, the general activist organizer or like, you know, your general data scientist person who wants to just edit the data or put the data somewhere. But I don't like it as a developer. So I want to try and solve that problem, although I haven't gotten there yet. And there are huge implications for open data. So we're applying for a grant right now with the Night News Challenge. We're going to try and break down open data silos. So we're building an application that lets you search and download across data portals. And when you search for the data across a data portal, it'll actually give you a nice interface as an app on your computer. And you can like download that data and it'll let you know when the data has changed, like Dropbox does. But it'll all be able to be interacted with JavaScript or Python. I'm building a Python library as well. So it'll be really easy for people like us to interact with people like my friends who use R in universities. So big thanks to these two. And they did a lot of the under the cover work. And if you have any questions or want to talk to me about building cool apps, we're really stoked about this new grant and might be looking for more people. So thank you very much.
Nope. Can I get that mic?
There's no mics.
Zero mics. Okay, we'll do this. Let's just wing it.
What? Wait, there's this thing. Just be like,
Yeah. Oh, we gotta move from here. You see. Thank you. Okay, great. So it seems like you have basically mastered everything in life. Is there a skill still unmastered, do you think?
yes.
Okay. All of them. Okay. All right.
It's hard to say.
Yeah.
I don't think I've mastered anything except for trumpet, probably.
Ah, beautiful. Next time, play it for us. How does it make you feel when people don't know what abstract level down is?
It makes me sad because we should have. Well, I actually don't care. It's fine.
Continue not knowing. If you could live in any historical decade, when would it be and where?
They're all kind of crappy for women, so I don't know.